Section 1.3, new functions from old functions. So in order to make a new function out of an old function, there's a number of things we can do, such as shift the function vertically and horizontally, or stretch the function vertically and horizontally, or even reflect the function. To obtain the graph of f of x plus c, we would move the graph a distance of c units upward, and similarly f of x minus c moves the graph a distance c units downward. However, if we subtract directly from x inside of the function, then we shift right or we shift left. That can seem a little bit confusing because adding c shifts upwards, whereas adding c inside the function shifts left. You would expect maybe for it to shift right, but if you move it to the other side, like instead of writing it as y equals fx plus c, if you wrote y minus c equals fx and y plus c equals f of x, then you can see those match with the upward and downward. So really it's pretty consistent if you think about the c modifying the variable itself instead of actually right next to the function. So if you think of it as modifying the y, then subtracting c from y moves you up because you end up growing a lot more quickly in relation to x. And similarly, subtracting c from x moves you to the right because then you end up growing a lot more quickly with your x value in relation to the y value. For vertical and horizontal stretching, if we multiply by a constant, then we shift vertically by a factor of that constant. So if this is the graph of y equals x squared, for example, then the graph for y equals 2x squared will grow twice as quickly, so it stretches up. Hopefully that looks a little bit more quick. And if we had the graph of y equals half x squared, it grows more slowly. So, so it gets kind of smushed a little bit. If we multiply by the x inside, then it shrinks the graph horizontally. If we divide by x inside, it stretches it horizontally. If we multiply by f of x outside by a minus sign, then it reflects the graph about the x-axis. So it's up or down reflection, which makes sense. You multiplying the y value by a negative, you would flip it up or down. And if you multiply the x value by the negative inside the function, then you reflect left and right about the y-axis. Okay, so let's do an example. Given the graph of y equals square root of x, use transformations to the graph y equals square root of x minus 2, y equals square root of x minus 2, y equals minus square root of x, 2 square root of x, and square root of minus x. So let's start with the graph of y equals square root of x. We're given that this graph just looks like that. Okay, so given that original graph, let's make this thing into square root of x minus 2. So we would just, we're subtracting from our function, which is the same as adding to the y value, so this thing moves down too. Not great. Okay, let's take a look at the graph of square root of x minus 2. I feel like if I can emphasize that in just the right way, maybe we'll understand the difference, but I don't. Okay, so then we're subtracting from x, so we move to the right. So that's 0, that's, let's say, 2. So this moves it from the original square root of x to the right. Okay, let's take a look. Oh, by the way, this one's bothering me. It's a little bit like too high. Let's try redrawing that. Yeah, that's a little bit better. Okay, let's do minus square root of x. So that flips it upside down about the x-axis. And let's take a look at 2 square root of x. That should make it grow twice as fast, so it gets a lot bigger, a lot faster. Oh, I forgot these. Okay, let's do last one. And this one is y equals square root of minus x, so it flips it left, right. Okay, let's move on. Let's sketch the graph of the function f of x equals x squared plus 6x plus 10. In order to do this, we could just plug in points and see what we get, but instead let's try to transform it from the graph of y equals x squared, just to practice making new functions from old functions. So we have y equals x squared plus 6x plus 10. In order to see how this is obtained from y equals x squared, let's complete the square. So this thing is the same as x squared plus 6x. We can complete the square by adding half of 6 and squaring it. So we'll add 9. But we're not allowed to just start adding numbers to our function, so we have to subtract off what we added. That way we're really just adding nothing. And keep our plus 10. So then this part over here is a perfect square trinomial. So that we can just write as x plus 3 squared. And then negative 9 plus 10 is just positive 1. So it looks like our graph is obtained by moving to the left 3 from x squared and moving up 1. So if I look at my original graph, this is going to be y equals x squared. Then I get my new graph by moving to the left 3 and up 1. So I should start over here. And this is the point minus 3, 1. Okay, let's sketch the graphs of these functions, y equals sine 2x and y equals 1 minus sine x. So in order to do y equals sine 2x, let's start with sine. Okay, so this is assuming that we already know that sine goes from minus 1 to 1, and it hits a maximum at pi over 2. It goes to 0 at pi. So let's see if I can draw that. Alright, it almost resembles sine. So that's my original y equals sine x. In order to get sine 2x, we're going to double inside the function. So that means that we're basically going to compress this thing because x is going to move twice as quickly. So we would expect to get this smushed horizontally. So that means instead of having a max at pi over 2, we now have a max at pi over 4. Instead of going to 0 at pi, we go to 0 even faster at pi over 2. Okay, let's see if we can draw this smushed guy. Oops, guess we can't. Okay, so you can see that it wiggles a lot more quickly, but it still has a maximum of 1 because we didn't move up or down or stretch, vertically at all. So that's y equals sine 2x. Let's do 1 minus sine x now. Okay, so again, starting with sine, what we'll do is we will multiply by minus 1 for sine of x, so that flips it upside down over the x-axis, so it flips it upside down vertically, up, down, and then we have to move it up 1. Okay, so it should have had a maximum pi over 2. So instead now, because we're flipping it up and down, it has a minimum at pi over 2. And instead of being 0 at pi, it's going to end up being 1 at pi. Okay, so this is 1, this is 2, has a new maximum of 2 now. Okay, let's see if we can do this. Okay, so that's roughly what it should look like. It gets flipped upside down, and then it just moves up 1. Okay, in example 4, the figure shows the graphs of the number of hours of daylight as functions of time of the year at several latitudes. Given that Philadelphia is located at approximately 40 degrees north, find a function that models the length of daylight at Philadelphia. Okay, so we're looking at this orange-looking one. Okay, so we have to follow the orange guy. It seems like the highest height, which is over here, is about 14.8 roughly. And it seems like, so that's the maximum. And our minimum, it looks like, is at the end. Maybe it's like 9.2. So first we can write our amplitude, which is our distance from our maximum to our minimum. So the amplitude is half of 14.8 minus 9.2, which is 2.8. Okay, so that's a distance from a midline. Our period, well, this thing is number of hours of daylight as functions of time of the year, so our period should be for 1 whole year. So 365 days. So let's do that. $365 days. Okay, let's see if we could figure out what b is in our function then, because 2 pi divided by the period is b. So b is 2 pi over 365. And then we're going to shift, it looks like, because we're not starting at January. We're starting around, it looks like, let's say, over here is where we start. For our x value, it looks like, let's say, March 21st, maybe. So that's 80 days into the year, so let's shift 80 days to the right. And And we're also not starting at 0, we're starting up in the air. It looks like we're starting at 12. So let's shift 12 hours upward. Okay, so now I think we have enough to build our function. Recall that we have our function is in general a times sine of b x, how about plus d plus c, where a is our amplitude, 2 pi over b is our period, d is our horizontal shift, and c is our vertical shift. So that means that we can come up with a function here. How about we use, let's see, this is supposed to be length of daylight. So how about we use length with respect to time, so it's L. So L of t equals 12 plus, because 12 is our shift upward, our vertical shift, that'll be C. I just changed the order a little bit. 2.8 for our amplitude, A, times the sine of B, which is 2 pi over 365. And that's times T. And our shift is to the right, so we're going to subtract 80. Okay, let's take a look now at what happens with absolute value functions. We have y equals absolute value of x squared minus 1. Let's take a look at what x squared minus 1 looks like. Okay, so it's just x squared, and then we just move down 1, so I don't think I have to actually draw x squared because we should remember what that looks like by now. So that's y equals x squared minus 1. That's a minus 1, that's 1. Okay, in order to write y equals absolute value of x squared minus 1, remember that absolute value doesn't do anything to positive values. They just stay positive because they're just distance from 0. But negative values get obliterated. They all become positive values. So that means that all of, let's see if I can do this, all of, let's say, these guys over here, these are all our negative values. Those are going to become obliterated. We're going to flip all of those and make them all positive. So drawing this, we still have our positive values as before, from 1, minus 1. However, all of our negative values get flipped because that's what absolute value does. So that's what they become. So this is y equals absolute value of x squared minus 1. Oops. Absolute value. Okay, let's talk about some other ways we can manipulate functions. We can add functions together by creating a sum function. So if we add f of x and we add g of x, we call that new function f plus g of x. Similarly, if we subtract two functions, we call that new function f minus g of x. And we have product and quotient functions defined pretty much exactly how you would think. F times g of x is just f of x times g of x. F divided by g of x is just f of x divided by g of x, assuming that g of x is not 0, because we can't divide by 0. We can also compose functions. So we call the composition of f and g, that's f composed with g of x, to be f of g of x. That means we just take f of x, and instead of evaluating it at some x value, we just plug in g of x for that x value. So let's do an example of that. if f of x equals x squared and g of x equals x minus 3, let's find the composite functions f composed with g and g composed with f. So f composed with g of x, by definition, equals f of g of x, which is f of, well, g of x is x minus 3, so that's what we're plugging in, x minus 3. Okay, so if we plug in x minus 3 into f, that means that whatever we plug into f just gets squared. So just x minus 3 squared. Okay, g composed with f now. So that's g of f of x by definition, which is g of, well, f is x squared, so we'll plug in x squared for g. And if we plug in x squared over here, that means that it's just x squared minus 3. So notice the order matters a lot. F composed with g is often not equal to g composed with f. Okay, if f of x equals square root of x and g of x is square root of 2 minus x, let's find each of the following functions and their domains. So first, f composed with g. F composed with g of x, by definition, is f of g of x, which is f of square root of 2 minus x, which is, let's see, we're plugging in square root of 2 minus x into square root of x, right over there. So that means that we're taking the square root of 2 minus x. So that's just the fourth root, 2 minus x, or 2 minus x to the 1/4 power if you like. Okay, our domain now. Well, we know that square roots are bad for negative numbers, so our domain is all of our x values such that 2 minus x is greater than or equal to 0. So that's the same thing as all of the x values. Well, 2 minus x is greater than 0 is the same thing as saying x is less than or equal to 2. Okay, so that's all of the numbers from minus infinity up until 2. Okay, let's do g composed with f. So that's g of f of x, which is g of square root of x, which is square root of 2 minus square root of x. Okay, we need x to be greater than or equal to 0 for this square root, but we also need 2 minus square root of x, this whole thing, to be equal to 0 or greater than or equal to 0 for the big square root to be defined. So we have both of these things. We have to be careful of x has to be greater than or equal to 0 and 2 minus square root of x has to be greater than or equal to 0. This is the same as saying that square root of x is less than or equal to 2 as before, so that means that x is less than or equal to 4. So our domain we can write now is all of our x values such that x has to be less than or equal to 4 and greater than or equal to 0, so it's just between 0 and 4, which is the interval from 0 to 4. So it's not defined for as many values as the other one was. Let's look at f of f. We can compose functions with themselves, why not? So f composed with f of x is f of x, which is f of square root of x. So that's the square root of the square root of x, aka fourth root of x. Okay, we already know that square roots are defined for values greater than or equal to 0, so fourth roots are the same. So it's all of our non-negative numbers. Okay, last but not least, g composed with g. So that's g of x, which is g of square root 2 minus x. So that's square root of 2 minus square root of 2 minus x. Okay, so that means we need 2 minus x to be greater than or equal to 0, and we need 2 minus square root of 2 minus x to be greater than or equal to 0. So we need this to be true, and we need this to be true. Okay, in this case, we have x is less than or equal to 2, and in our other case, we have this thing is less than or equal to 2. So that means that 2 minus x is less than or equal to 4 when we square both sides. So that means that x is greater than or equal to minus 2. So our domain is all of our x values such that negative 2 is less than or equal to x is less than or equal to 2, aka x is between minus 2 and 2. Okay, let's do another example. What if we want to compose 3 functions? Okay, let's find f composed of g composed of h if f of x is x over x plus 1, g of x is x to the 10th, and h of x is x plus 3. So f composed with g composed with h of x is f of g of h of x. So that's f of g of x plus 3, right? Because h of x is x plus 3. And now we have to plug x plus 3 into g of x, which is x to the 10th. So that means we're just going to take x plus 3 and raise it to the 10th. So that's just f of x plus 3 to the 10th. Okay, so that means we're plugging x plus 3 to the 10th into each of these x's, because now we have to plug it into f. So that's just x plus 3 to the 10th divided by, instead of x, x plus 3 to the 10th, and then we keep our plus 1. Okay, looks worse than it is. Okay, let's see if we could find functions f, g, and h such that big F equals f of g of h, when big F is cosine squared x plus 9. Well, this is a fancy way of saying the cosine of x plus 9 squared. That's what we mean when we put the 2 right next to cosine. So we want to find functions that, well, let's start from the innermost part, kind of like PEMDAS. First, we can look at what's happening in here, which is x plus 9. And then it looks like we take the cosine of that. And then it looks like we square it. So we start with this function first, then we apply the next one, and then we apply the last one. It's a little reversed order. So we're going to start with h of x equals x plus 9. Then we'll take the cosine of it, and then we'll square it. So let's look at that. Let's test it, make sure it works. So f composed of g composed of h. That's f of g of h of x. And that's f of g. Let's see, we made hx plus 9. And we made g cosine, so that's cosine of x plus 9. Okay, well that's nice, because f was just a square, so that's cosine x plus 9 squared, which is just capital F of x. Exactly what we wanted.